Something may have grazed us. A long time ago, before stars existed, before atoms had fully formed, something brushed against the fabric of our universe. Not a collision, not an explosion, a graze, a touch so vast and so slow that the scar it left behind is still visible today, written into the oldest light in existence if you know how to read it. The idea that another universe could be close enough to touch ours is not a metaphor. It is not science fiction, it is a prediction, a serious, mathematically grounded prediction that emerges from some of the most tested theories in modern physics. And the evidence, thin as it is, points towards something that most people are never told. We may not be alone in the way we assumed. Not in the galaxy, not in the solar system, but at the deepest level of reality itself. To understand why, you have to go somewhere most explanations stop short of. We think of the universe as everything, the total container of all that exists. But in string theory and its extensions, frameworks that physicists have spent decades refining, not because they're fashionable, but because they keep producing mathematics that works. The universe we live in isn't a container at all. It's a surface, a membrane, a vast three-dimensional sheet drifting through a higher dimensional space that has no name in ordinary language. Physicists call it the bulk. And if our universe is one membrane drifting through the bulk, there is nothing in the mathematics that forbids other membranes. Other universes parallel to ours, separated not by distance in the directions we can move, but by distance in a dimension we can't perceive. Close in a way that makes no intuitive sense. Separated by a gap that might be extraordinarily thin, thinner in some models than the width of a proton, yet completely invisible to us because we are confined to our membrane. We cannot look sideways into the bulk, we can only exist within our own sheet of reality and wonder what drifts beside us. This framework is called brane cosmology, and it does something that most cosmological theories struggle to do. It offers a physical mechanism for how the universe began. In the standard picture of cosmic origins, everything starts with a singularity, a point of infinite density where the known laws of physics break down. We call it the Big Bang, and we understand what came after it remarkably well. But the moment itself, the very beginning, remains a wall. The equations fail. The physics we have cannot describe it. Brane cosmology offers a different picture. In some versions of this framework, the Big Bang wasn't a beginning at all, it was a collision. Two membranes, our universe and another, drifting through the bulk, drew close enough to touch. The energy released by that contact was catastrophic, beyond any scale we have words for. It heated our membrane to unimaginable temperatures. It set matter in motion. It became everything we know. The Big Bang in this picture was not the start of time. It was an impact, and the other universe that struck us or grazed us may still exist, drifting away or drifting back. The model that formalizes this is called the ekpyrotic universe, developed by physicists Paul Steinhardt and Neil Turok in the early 2000s. It's a serious proposal, peer-reviewed and mathematically rigorous, that reframes cosmic history as a cyclic process. Universes on adjacent membranes approach, collide, rebound, drift apart, and eventually approach again, not once, repeatedly. Over timescales so long that the word cycle barely captures it, each collision produces a new Big Bang. Each Big Bang produces a new cosmos. What we experience as the beginning of everything may be one beat in a rhythm that has no known start. The part that makes this more than philosophy is this: it makes predictions. And some of those predictions concern marks that would have been left on the universe if a collision occurred. The cosmic microwave background, the ancient light that fills the entire sky, the afterglow of the early universe carries patterns in its temperature. These patterns reflect the conditions of the cosmos when it was only 380,000 years old, and they match our best models of early physics with extraordinary precision. But there are anomalies, features in the CMB that don't fit the standard model cleanly. A large cold spot in the southern sky discovered by the WMAP satellite and later confirmed by Planck that is statistically unusual, a suppression of fluctuations at large scales that the standard inflationary model predicts shouldn't be there, an alignment of certain temperature patterns that seems too ordered to be random, None of these anomalies are conclusive. Scientists are careful with that word. They could be. Statistical accidents, artifacts of incomplete data, or features of our own galaxy contaminating the signal. But they are real features of the data, and some researchers have noted that they are consistent with what you would expect if our universe had at some point been deformed by a neighboring one, pressed, nudged, or struck in a way that left an asymmetry across the sky. A bruise, some have called it. A bruise on the universe. That word does something. It makes the abstract physical. A bruise means contact. It means something was here, close enough to leave a mark, and then it moved on. Or it's still there. The honest position is uncertainty. We don't know if the CMB anomalies are echoes of a collision. We don't know if brane cosmology is correct. String theory, the framework it depends on, has not yet made a prediction that an experiment has confirmed or refuted in a clean, decisive way. This is one of the deepest tensions in modern physics, a mathematically rich theory that may be describing something real and fundamental, but that has so far resisted the kind of direct experimental contact that science requires. But here is what's worth sitting with, regardless of how the physics eventually resolves. We have, at this point in history, constructed mathematical frameworks in which the universe we live in is not the only one, in which other universes are not only possible, but necessary, in which our own beginning might have been caused by contact with something we will never directly see. And we have found, in the oldest light in the sky, features that we cannot fully explain, features that are at least consistent with the idea that something was here before us, or beside us, or is beside us still. That is not a story we invented. It came from the data, from the equations, from people spending careers in quiet offices, working through the mathematics of dimensions we cannot enter and timescales we cannot survive. And somewhere in those equations, in that ancient light, in the cold spot that stretches across a patch of sky that has no obvious reason to be cold, there is a question that refuses to close. What if the collision left more than a bruise? What if it left a memory? Not in any conscious sense, but in the structure of the universe itself. A slight asymmetry, a faint preference in the geometry of space, a whisper encoded in temperature fluctuations of something that was close enough to touch us and then was gone. We point our instruments at the sky and we measure, we refine, we look for patterns in the noise and try to separate the signal from the accident. And sometimes, in the most careful readings of the most ancient light we can detect, something looks back. Not a face, not a signal in any human sense, just a shape in the data that doesn't quite fit, that sits outside the standard explanation, that science marks as anomalous and moves on from because there's no clean answer yet. But it's there, and if it means what some physicists believe it might mean, then the universe we think of as everything, the totality of existence, the whole of what is real, is pressed against something else, something parallel, something we cannot see or enter or measure directly, something that may have made us and may still be there.